Hey there, my name is Alejandro, and welcome back for day 130 of me doing the Daily LeetCode challenge after I reach 1 year's worth of good contributions here on GitHub. So today's problem is from November 23rd, 2024. Let's get straight into it. Okay, today we got LeetCode medium problem 1861, rotating the box. Alright, we're gonna get a box, we're gonna rotate that box. You're given an n by n matrix of characters box, okay, representing a side view of a box. Understandable. You know, this is a 2D matrix. A side of a 3D box is indeed 2D. Each element of the box is one of the following: a stone, a hashtag, a stationary obstacle, a multiply sign, or empty, a dot sign. Okay, the box is rotated 90 degrees clockwise. Oh lord. Okay, causing some of the stones to fall due to gravity. Oh. Okay, wait, this is actually going to be kind of annoying. Okay, each stone falls down until it lands on an obstacle, another stone, or the bottom of the box. Gravity does not affect the obstacle's positions, and the inertia from the box's rotation does not affect the stone's horizontal positions. Gravity does not affect... I'm already thinking, by the way, like if you rotate 90 degrees, it's as if though gravity is being pushed this way, right? Where it's like if I have a box, right? Like here, gravity is going down this way. Now, if I rotate this 90 degrees... right? Gravity is pushing down on this. Oh, so it's not going to be as simple as just pushing down here. So it's as if though, yeah, it's as if though gravity is coming here, right? It's pushing down on here, down on here, down on here, down on here, down on here. So if I have this not rotated, it's as if though gravity is coming from over here, right? Where it's like if I have this little boy here, right? And I have this little boy, okay, or if I have this like this, right? It's like I rotate it this way, then it's like gravity comes from top to down, right? So from top to down, right? So if I derotate this thing, it's coming from this side. And this is where the beginning of the rows are. So, okay, that makes sense. So essentially, it's like, yeah, if I rotate that, it'll go down, which if I go back is as if they're going from the start of the rows to the right is where gravity is being influenced from. So we can think of gravity as going from left to right instead of top to down because, again, we're applying gravity after we do a 90 degrees clockwise turn. Okay. Gravity does not affect the obstacle's positions, and the inertia from the box rotation does not affect the stone's horizontal positions. Okay. It is guaranteed that each stone in the box rests on an obstacle, another stone at the bottom of the box. Okay. Return an n by n matrix representing the box after the described rotation described below. Okay. So here we can just do something like this. We can say, you know, self.box for row index in range length of the box. Return, yeah, we'll do self dot apply gravity, left gravity, left right gravity, right? Where it's like, okay, let's look at an example, right? Just to make sure that I'm not tripping here. Let's look at a box. So hashtags are stones, right? Okay, so like this stone should surely come here. Oh, wait. You do return the rotated matrix at the end of the day. But it would have still worked, right? Where it's like essentially what I'm saying is if I have a box like this. Okay, wait, since at the end of the day I'm rotating this, I can just, you know, do columns instead of rows, right? And just do gravity normal, right? Okay. So yeah, instead of applying gravity from left to right, okay, I can essentially scrap that. I can just rotate the matrix and then apply gravity, right? How do you transpose a matrix in Python? Oh gosh, okay. I don't want to make myself look up stuff, but I'll have to think. What is it even a transpose? No, a transpose is different than a rotation. Oh, wait. Wasn't there like a medium LeetCode problem that was like rotate a matrix and the solution was literally to do a transpose plus a reversing of all the rows or something like that? That could make sense. Okay. I remember that just from like a Nick White video like a couple years back. Okay, so my idea was essentially if I do something like this, I apply gravity from left to right. So like this is empty, so this becomes the hashtag, and this becomes the dot, right? And then if I rotate this, right, I essentially have a dot at the top and the hashtags at the bottom, right, which is exactly what you want, right? This is exactly what I'm saying. It's like if I have something like this, right, I'm not even going to look at the output yet. If I have something like this, the point is that I apply gravity left to right, right? So this remains an obstacle, but this guy would fall over here, right? And this becomes a dot. And then these guys are already done as follows. And then what I'd have is like, you know, dot hashtag, or hashtag dot. Like the point, I have to think about this. Yeah, so this will be hashtag dot, hashtag, star, dot. Is that what they have? Yeah, hashtag dot, hashtag, star, dot, right? So yeah, that's the point. So yeah, I have to rotate the matrix anyways. So I might as well rotate it, right? A rotation can be kind of annoying, I'm not gonna lie. We can also do the thing where it's like, I can apply the gravity left to right first, just to essentially convert the problem into just rotating a matrix, right? Because I want to make sure that I do that step correctly. So I might as well do, you know, applying left to right gravity and so on. Which means that essentially what I need to do is look from the right of a row, right? I see a column, a stone here and so on. If I see a stone or an obstacle, it stays there, right? But then if I see an empty spot, it's like, oh, okay, this is where like the next stone will go, right? Or it's like, if anything, I can start using a stack to, oh no, I should use like a queue, right? Where it's like, you know, I append something early, like this dot here, which is like, you know, the next thing to fill, right? And then when I see a stone, it's like, okay, I pop from the left hand side of the queue because that's the first empty slot that I saw, right? So okay, so essentially, okay, let me write a function that says like, you know, def this takes in apply horizontal gravity. And this will take in a box row, right? And this will be okay. So we will use a queue is equal to collections.deck, right? This is double-ended queue, right? And then we'll say for item in, okay, so we'll do range, we'll do length of row -1 all the way up to -1 non-inclusive and backwards. We'll say if okay, as soon as we see a stationary obstacle or a stone, we essentially reset everything, right? Okay, first of all, if item is equal to this, first of all, yeah, assert that, you know, item in, it's either a hashtag, you know, a star or a dot for now. If item is equal to a star, oh, is LeetCode doing the, no, it's not. Okay, if item is equal to a star, then what are we gonna say? We're gonna say, no, a dot, right? Okay, I'm just gonna do this, stone, obstacle, comma, empty is equal to hashtag, star, and dot. Here we'll do in stone, obstacle, empty. Item equal empty. Then we'll say that, hey, since this is an empty item, actually, for I in range this, item is equal to row of I. If item is equal to empty, then we'll do q dot append index I, right? And here continue. Just in case, let's just do this. This is no longer empty, right? So now we have stone or obstacle. So if we see an obstacle, it's clear, right? If item equals obstacle, then queue, is there a clear function or should I just initialize this to a new queue, right? So if I do Python 3 I do import collections. Q is equal to collections.deck, right? And I do q.append I for I in range, 25.1, right? Q is this, right? Length of Q, what? Q.pop. For I in range 251, q.append left I, right? There you go, Q. Now if I do q.clear, okay, so there is a legitimate function. So here I can do q.clear. Okay, I was like, do I need to initialize this to something new? Although q.clear, I mean, surely they make that efficient, right? I mean, I guess like Python has to like garbage collect anyways and so on if you initialize it to something new. Like surely they just make that efficient, right? To do, check if reinitialization is faster, right? Maybe like garbage collector is faster than I am. I wonder how they optimize a function like this, right? Because the point is like, I have a bunch of indices, but if I see an obstacle, then anything that was in the queue, like a stone cannot reach, right? Insert item equals stone, right? Because here we're going to do continue. If length of Q is greater than 0, right? If it's not greater than 0, that means like, the stone is at the bottommost, i.e. rightmost position it can be here, but we're applying gravity horizontal, so that's why it's rightmost, not bottommost. If length of Q is greater than 0, that's good. Then it can swap with a position, right? So new index, new stone index equals q.pop left, right? So here we'll say row of new stone index is equal to well, stone obviously. Index is equal to this. Assert that row of index equals empty. Row of index equals stone. That row of I equals stone. Right, but item is equal to row of I, so that's already true, but whatever. Then row of I equals empty. And since a row of I is now an empty one, q.append I, right? Another stone can go in here if it absolutely needs to, right? And here, I'll do return row, right? Okay, so right now I want to try something like this. Also, this should definitely go inside of here. Whoopsie daisy. Horizontal gravity on row for row in box, right? So for now, we're not doing things efficient, and this is not going to work because obviously I'm not rotating the matrix here. Yeah, this should take in a self. Okay. Well, this is good, right? I have the unrotated version of that solution, right? Here, I have, so let's think about it. Let's think about it. Let's think about this. Let's think about this, right? If isn't this what zip is good for or something in Python? I gotta remember. Is it literally just zip, something like this? I don't know if this is right. Oh, so do I have to make this an array of its own? I forget how zip works. Yeah, I forget how Python zip works. I remember you could use this somehow for transposes. Yeah, because if I return this, what do I get? What if I zip this guy? Interesting. Oh gosh, that's definitely not gonna work. Okay. Yeah, I don't remember how to use list. Not to use zip. Maybe it's zip of the zip. Yeah, I forgot how to use this function in Python. That's a rip. That's a rip. That's a rip. Because I can probably use it in a way that's needed here. But yeah, I forgot how to use this thing. I use this in my functional programming class, and so, but yeah, I forgot. But no, not a worry in the world. We can still just do a regular rotation and the way that we need to. I remember it was like like we were learning Racket and it was like apply map list m or something like that would give you the rotation or transpose of a matrix, one of the two. And it's like with Python you had the zip function that you could apply similar things. But okay, yeah. Oh yeah, by the way, oh, it's doing like this because it's like oh yeah. Okay, I can probably figure out how to use zip, right? Okay, so let me try, right? If I have r is equal to 1 2 3 and I do zip of r, list of zip of r. Okay, so if I do zip r dot copy, oh my gosh, list. Okay, so if I have two lists together, essentially, okay, so it is essentially kind of what I want, right? Where it's like, yeah, you feed it multiple lists, right? But you need to feed them as yeah, so that's the problem. You can't feed it as one singular list. So zip r1 equals r dot copy, r2 equals r dot copy. So zip I for I in r1, r2. List of this guy. Yeah, it doesn't work the way that you want. How do you deconstruct things in Python, right? Can I do star here? Oh, is that it? Okay. If I do star 1, 2, is that how you do it? Okay, because that clearly gave me the result. I remember there was something like this. Okay, if I return zip, so I put this like this, but I destructure them. Okay, so for something like this, it did like it. For something like this, it does not like it. Oh, so I have everything in flipped order, right? So maybe I do this in reverse and this works. Okay, and if I submit, does this work? Okay, ladies and gentlemen, we figured out a way to rotate a matrix only using zip. Okay, I was literally gonna do. I'm pretty sure there's like a LeetCode medium problem, which is like rotate a matrix 90 degrees clockwise, and I'm pretty sure the way that you do that is you do the transpose of the matrix, right? As well as you do a transpose of the matrix, and then you reverse all the rows, right? So we could try to do something like this. Was like here I can take that same result, right? So, you know, I can do res is equal to this. Oh gosh, okay. So here obviously return zip of star res works, right? Right, and so here it's like, okay, I could do step 1, transpose res, step 2, reverse rows of res, right? So step 1 is transpose. It's like, okay, for I in range length of res, for j in range I plus 1 length of res of I, right, or something like this, because I don't want to flip things twice, right? So here I do res of I j comma res of ji equals res of ji res of I j. So here it's print res, print, apply transpose, print res. For row in res, print row. And then same thing here. Right, and for now we just return, you know, res, which is incorrect, right? But that's not the point. Length of res of I. Okay. Right, the point is that, like, you know, ij becomes ji and ji becomes ij. But how do you transpose a non-square matrix essentially is the problem. Right, so like if the dimensions are not n by n, this actually makes your life annoying, right? So yeah, I guess essentially it's like, you know, you could create so here we can do new res equals m n equals length of res column 0. New res is equal to, you know, 0 times n this time for this in range m. So the other way, right? So here we'll do new res of ij is equal to res of ij. So here, okay, I gotta be careful that I do things correctly. I don't think I am right now. Yeah. I don't think I is sufficient, right? Might be in these cases, but not necessarily these cases. Yeah, these have negative 1s in them, right? But what if I do length of res of I? Right. So here I have star, dot, yeah, so that's perfect. So here I have dot, oh gosh, dot, star, wait, oh. And now this is J I. So yeah, now I've applied transpose, and these are the new values. And so this one is correctly done because there's only length 1, but all the other ones need to be reversed, right? Yeah, so these guys, or they don't need to be, because it's reverse of reverse is already done, right? Okay. Because again, here we needed to reverse our solution. So, okay, this is a lot to think about, not gonna lie. Dot. Okay, it seems like we have our solution, right? Like here, I can just return new res. Okay, so that also works. Okay. So, okay, that's cool. So here, for some reason, we don't need to do the reversing. I guess because of like, the, or is it rotate an array counterclockwise that you needed to do the reversing of the arrays? Maybe that was what it was. But I remember there being a problem in LeetCode where it was like, rotate something clockwise, rotate something counterclockwise, and the idea was transpose and reverse the rows. Here, I guess we don't need to do the reversing, right? But there's probably something we can do. Oh, wait. We do need to do the reversing. It's just that here I was cheeky and I reversed res. So here I was cheeky and I reversed res. So here we're gonna do return an array with, row backwards for row in new res, right? And then that works. In new res, sorry. Okay, yes, and that is the idea. Okay. So I was not going crazy. Here, again, we might get a very slow solution. We're printing stuff too, blah, blah, blah. But again, okay, I'm not going crazy. This is essentially the intended idea, where it's like if you want to rotate a matrix regular clockwise, to do so, you can essentially transpose the matrix and then reverse every row. Again, I remember that because I think it was Nick White a couple years ago. He posted a video where it was like some Amazon question. I think it's like one of his most viewed or most liked videos on his channel. So like, it might be like, if you go to Nick White's channel, it might be like one of his top 10 highest view videos. It's like some Amazon problems, like, rotate a matrix, clockwise. Because I remember that being a very popular Nick White video that, always stuck with me to the end. But we can also do zip in order to apply the things that we need. Okay, so, which essentially means, yeah. Yep. But essentially, we can just return this instead, right? Yep. So, okay. Okay, so that's a little bit faster. So here we can do... okay. We have ways of doing this faster, right? So let's get rid of this. So this is a rotate the box, right? First of all, we don't need to be doing... also, yeah. So another thing we can do is check... First of all, if I do q is equal to collections.deck, does that make things faster? I always misspell this. Collections.deck. Did it? Okay. It seemed to make me a bit faster. Or it doesn't really matter. 1940 versus this. Okay, yeah, q.clear is fast enough. Also, we can get rid of all the asserts, so the asserts can become hashtag asserts. I can also get rid of the continues. And I can make these if-else-if clauses. Right, also... Here I can take a row index. Box of row index. Right? Here I can do row is equal to box of row index. So here in length row. There we go. And range for row index, length of box, self dot apply this box comma row index, and now I have modified box. So here we can return zip star star box. Does that work? No, not quite. Length of box. So box backwards, right? So that'll work. Yeah, so this works. Does that make things faster? It kind of makes them faster. So to modify things directly. Ooh, okay, now we're at 92%, okay. And we can definitely also, so okay, modifying the box also makes it fast. I wonder if we also did something like, you know, if I reverse a lot of these operations. Okay. So this works. Okay, also let me go back to the other solution just in case. Okay, just because I want to have this. So let's comment this out. And here, let's paste our new solution. And so here, I just want to try something. So this works. So here, let's do this. Instead of making things backwards, we shall do box of row index for row index in range length of box -1, -1, -1. Does that make me go faster? Right? So now it's just like I go in the order that I actually want. Ooh, and there we go. Okay, now we're at 99.68%. Okay, and this, honestly, I might as well keep this as a comment because it's technically another way that I did the solution and so on. Okay, this actually, okay, 99.68% is absolutely as close as we can get to a fast solution. We're over here at the peak, which means I'll make a good phone call to Nor and be like, well, what runtime did you get, sir? Huh? Did you beat 99.68%? Don't think so. Well, maybe he does, but yeah, he definitely knows zip as well and stuff like that. So yeah, maybe he beats me, but okay, that definitely feels good, 99.68%. But nevertheless, as always, in all my videos, I do a quick recap of how I was able to solve the problem. So for this one, essentially, I even forgot my idea. I was focused so much on just doing like you know, the matrix actual rotation part of the logic. But okay, yeah. So the very first thing that I realized is like, hey, if I'm gonna take a box, right? Let's pretend that this is my box here, right? Or maybe I can use an actual box, right? So let's take something like this, right? Here's an actual box. This is a box of Bear Bell's protein bars. So if I take this box, right, and I'm going to rotate it 90-degree clockwise, right? So I'm doing it in the way that it's for you guys, right? Because clockwise for me is actually this, but like for you guys, this is what looks like clockwise, right? So this looks like a clockwise motion. So if we think about gravity, gravity is coming down from this angle, right? And it keeps coming down from this angle. And so if I rotate this clockwise, it's as if though we want it to come from this angle, right? And if I have this like this, right, that means that like this is where gravity is being inserted from. If we think of this as the matrix, right, this coming from here, gravity coming from here, means that essentially we're having gravity being pushed in from here onwards this way, right? From the left, right, all the way up to the right, right? From the left of the matrix to the right of the matrix, right? So that's essentially the idea that I uncovered. Whereas, oh, whoa, that just turned dark on me. But essentially the point is that, like, okay, if we rotate the box 90 degrees and apply gravity from top to down, that's the same as not having rotated it 90 degrees and then applying gravity from left to right, right? The only thing that I didn't realize is that at the end of the problem, you actually have to return the thing transposed. So you might as well just, you know, transpose the matrix first and then apply the gravity, which I think would have made the solution a little cleaner, a little more sleek. But I didn't do it that way. And it's just like, I was like, okay, so technically if we want to simulate gravity, we can do it from left to right instead of top to down. And then I didn't realize that you had to you know, give the transposed matrix. So I was like, okay, you know, I already applied gravity from left to right. Might as well just transpose it now, and it'll be the same result anyways, right? But so that's essentially what I did. So it might be a bit confusing, but essentially at this point, you know, gravity, I'm writing it to be from left to right instead of from top to down. Because again, like, you know, if you have this and, you know, gravity is coming from here and you rotate this 90 degrees clockwise, gravity is still coming from here, which means that if you think about it in terms of back when it was here, right, if I have my gravity finger here pointed like this and I unrotate it, it's as if though gravity was coming from here, right? And if this is the matrix right here, it's coming from the left-hand side of the matrix down over to the right-hand side, right? So essentially gravity is being pushed from left to right, right? So essentially when I wanted to apply gravity first, you can either rotate the matrix and then apply gravity top down, or you can think about how it would have been applied, which is what I did. So it's like as if though you apply gravity left to right, left to right, and then once you've applied the gravity left to right, you can just, you know, rotate the matrix and it'll be the correct solution. I think the more intuitive way to have done this is rotate the matrix 90 degrees and then apply gravity, but that's not what I did because, again, I didn't realize that you actually had to rotate the matrix as part of the solution. So this is why I coded it horizontally, so I'm sorry if this causes some confusion. I'm sure the editorial probably did not do it this way. But okay, it's the same idea nevertheless. It's just, okay, we're applying gravity from left to the right. And here what I said is like, okay, first of all, let's denote these symbols: stone, obstacle, and empty, hashtag, star, and dot, because I don't want to think of them as like, you know, this is a stone, whatever, and so on. Let's just write them out, right? And the idea is very simple, where it's like, okay, if we're going to think of this as like, you know, left to right, right? If we're going to take an example like this, right? If our gravity is shoving in from left to right, then that means like, hey, this is a stone, right? And so here at the bottom we have a stone, right? So that's going to stay itself. But here we have an empty slot, right? Which means that a stone might fall to the slot, right? Because if a stone falls here, then it won't fall past the stone because the stone is already here, right? So this stone might be able to fall all the way over to this empty slot, right? And so we have to consider this as like, okay, whenever we find a stone here, we recognize that, hey, if this is the first stone that we have found from the right-hand side, it will go to the very first empty slot that we have found, right? And if we have multiple empty slots, right? Sorry. If we have multiple empty slots and multiple stones here on the left-hand side, right, it'll be the case that this stone goes all over to this empty slot, right? And that this stone goes on over to this empty slot, right? So, and whenever there is an obstacle as well, right, then we essentially say like, hey, this will be, you know, top of the stack, blah, 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 right? So maybe we do something like this, right? And so here essentially what it's like, okay, let's keep track of a double-ended queue where we're going to keep adding empty positions to the right-hand side of our queue, and on the left-hand side of the queue will be the earliest occurrences of you know, empty signs that we have found, where it's like, hey, if we find a rock, we know it'll fall down to this, right? The only thing that can essentially stop us is if we find another rock, or we find, in which case it's like, hey, again, we always consider the first rock, in which case it'll always be at the bottom, right? So we don't have to worry about rocks too much, right? So for example, inside of my code here, whenever I see a rock, what do I do when I see a rock? Oh, okay. The rock logic is actually a bit complicated, right? Because when you see a rock, the point is you want to make it fall down. Okay, but the point is that otherwise, like, whenever you search through the thing, whatever rock you see first, you always finalize its result, so it doesn't interfere with any of the other rocks ahead of time, right? Essentially, when I take this, right, and I put it over here, right, then this becomes empty again, but then this rock will no longer interfere with this rock over here, right? And that's the point. And the point here as well is that this rock, hey, it landed here and not here because again there's an obstacle in the way, right? But the point is, like, once I finalize, you know, the result for a rock like this, then this rock will not interfere with any of the rocks that follow, right? So that's essentially the idea I was trying to convey. But the point is I keep track of a queue, right? And so I have things to the left and the right of the queue. And the point is that, like, I will always add to the right of the queue. That way, whenever I pop from the left of the queue, it'll always be the earliest occurrences of empty symbols that we see, right? I will only store the indices of empty symbols, right? So here we'll start off. We'll have this is index 0 here, right? Here is index 1. Here is index 2. Here's index, 3. Here's index 4. Here's index 5. And here's index 6, right? So here we'll start off our count from the very right, because again, we're simulating gravity falling down this way, right? It's falling from the left to the right, again, using the same box example. So like here's the bottommost, you know, it's as if though this is the top and this is the bottom, right? I'm applying gravity left to right instead of top to top. And then the way I do this is like, okay, whenever I see a stone, then it's like, okay, is my stack empty? If it is empty, that means there are no empty positions for that stone to fall to, so it's the deepest possible spot that it can be at, right? So that makes sense. Now, if I see an empty sign, it's like, okay, I see an empty symbol. A rock could fall down to this position, right? So here we're going to say, okay, at index 5, there is a rock that might be able to come at index 5. So we add that to the right-hand side of our queue. Since the queue had no elements, it's just the very first and last element, both of them, right? But the point is we add to the right and pop from the left. That way, when we pop from the left, we'll essentially pop the earliest occurrence of an empty symbol that we have seen, which will always be the highest index, which is i.e. the deepest possible spot, which is where we want the rock to fall to, because again, we're parsing this from right to left, where gravity is being applied left to right. And so then here, you know, I might have, like, let's say, you know, for the sake of example here, I add, you know, a couple more things here, right? So here's like, this was actually index 7. And so here I put like, you know, this was actually index 6 that we first found. And then when I traverse here, it's like, okay, index 5, we see another dot here. So that's another empty symbol, right? And so I put a 5 at the right-hand side of my queue, right? And so that way, it's like, if I see a stone, I will pop left and put that as the position where the stone falls into, i.e. this one, because it's the deeper position, right? So let's make that clear. Now, I come in over to index 4 from index 5 and I see, oh, there's an obstacle. When there is an obstacle, right, each stone from the left will at best, you know, fall down to this position, right? Because again, this does not get moved by gravity. So any stone that falls down due to gravity will stop here if they reach this index, right? They will not go on over to spaces 5 and 6 because again, there is an obstacle in their way, which will not fall down with the rest of the stones, right? So here what we do to simulate that is say, hey, these options are no longer valid for stones to fall into. So we clear the entire queue no matter how large it is. So that's why in my logic here, I say, hey, if the item is an obstacle, clear the queue entirely, right? And then from that point on, it's like, okay, we see an empty spot. So we append to the right of our queue 3 because that denotes an index that, hey, a stone could fall into, right? Then we go through here, we see another empty spot, we append that to the right of the queue, right? Then we see a stone. So finally, we see a stone. Now, when we see a stone, we do a couple things, right? So first, we check if the queue is empty. If the queue is empty, which was the case for this stone over here, then we say, hey, there are no currently empty spots for the stone to fall into, right? For example, if we had a stone right at this position, the queue would have been empty because we just cleared it with this star sign, and that stone does not get moved, which is good because again, it's at the deepest position it can be. In this case, it's like there are indeed empty slots that the stones can go to, right? But which slot do we want the stone to go to? Well, we know that it falls due to gravity. We notice that the first stone that we see up to this point from the right-hand side where gravity is being applied left to right. So we're like, okay, we want the stone to go to the deepest possible position that it can go through. Well, since we're adding the indices from deepest to shallowest, right? Where it's like gravity is going down this way, so this is like the deepest possible index, this is the shallowest possible index, then the deepest index will be at the beginning of my queue. Because whenever I see a new index, I write going shallower and shallower, right? From right to left, I'm going smaller and smaller indices. I'm always appending to the right of my queue, right? So the deepest, you know, deepest indices of empty slots are going to be at the beginning of my queue. So here I'm going to pop from the left-hand side, right? I'm going to say, okay, index 3 is now, you know, where I want the new stone to be, right? So essentially what I'm going to do is I'm going to take this stone and get rid of it, right? So one of the first things I'm going to do is that at this index, index 1, I'm going to replace this with an empty symbol, right? Because there's no longer going to be a stone there because this stone is falling. It's going to fall all the way down to index 3 because that's the deepest valid index that I can fall to. So I make it go to index 3, right? And that's essentially the part of this algorithm, right? Whenever I see a stone, I say, okay, if the length of the queue is greater than 0, then pop left because, you know, that is the deepest index that I have. I'm going to make that index a stone because the stone is now going to fall to that index. The index that the stone was originally at is now empty because the stone just fell from there. And then at the end of this, I'm like, okay, yeah, q.append I, right? Because it's like I is now an empty slot that another stone can fall into. In this case, like, you know, there's going to be one stone that falls into index 2, but if there were even more stones and so on, then this becomes a new empty slot that another stone could fall into. So technically, I append slot 1 over here, right? But the point is I keep doing this over and over. So here at the very end, I get to index 0, and then it's like, okay, from index 0, it's like, okay, where do I want the stone to be? It'll be whatever I pop here. So I pop that. So this becomes a 2, right? This stone now falls all the way over to index 2, right? And this becomes an empty slot, which means I add it to my queue here in terms of, like, you know, empty slots that, like, following stones are able to legally enter. In this case, you know, we've exhausted all the indices, so this becomes the gravity applied row from then on, right? And the point is that I apply gravity from left to right, so then all that remains to happen is I actually need to just rotate the row, right? So like which example was this? Was this example 2? Was this example 3? Stone, ... I forget which example this is. Which example did I pick this up from? Oh, I made this example on my own. It's not from here, right? But the point is that, like, once I rotate this, then I'll have the final result that I want, right? So now that we understand, like, you know, how I applied the gravity left to right, essentially I use the double-ended queue to keep track of valid empty slots that stones could go into. Whenever I see a stone, then great, you know, if the length of the queue is greater than 0, then I make that stone fall to its new position by popping from the left. Otherwise, if I see an empty slot, okay, that's another slot that a stone can go into, so add that to the right of the queue as the newest, you know, and shallowest, you know, empty slot. And whenever I see an obstacle, then it's like, okay, clear the entire queue, because everything that is in my queue are empty positions that are no longer valid for stones to fall to, because again, they'll fall to this position, right? So that's the point. For every single character, I know what I'm going to do with my queue, and there we go, bada bing, bada boom, right? So essentially now I'm able to apply gravity leftwards in the direction that I want, right? And so I've applied gravity for every single row, right? So I apply horizontal gravity for each row index inside of my box, right? And so here what I did is like, okay, now you have two ways essentially to solve the rest of the problem, which is essentially you just need to rotate the matrix 90 degrees clockwise. So one way you can do it is just by using the zip function. And I know this is like, you know, this is black magic, right? You destructure this list and so on. So if you don't know what zip is, don't worry about it. Here's essentially how you could have done it. So another way you could have done this is essentially to rotate a 2D matrix by 90 degrees clockwise. There's a little trick that you can do, which is essentially you can take the transpose of the matrix, which means that, you know, for every single index I, comma j, you know, box of I column j becomes, you know, box of j I. Right, so essentially it's like, you know, you flip the dimensions of the matrix, you create a new matrix with the flip dimensions, right? Instead of m rows n columns, it's now m columns n rows, and it's going to be, and you know, for every single index ij of the old box, now it's going to be the value at ji, right? And so that's essentially how you transpose a matrix. And once you transpose that matrix, right, all you need to do is reverse every single row inside of the matrix, and then you'll have made the matrix, you know, rotate 90 degrees clockwise in the end, right? This is just a small trick that I learned from a channel called Nick White. It was one of his most popular videos, I believe, where it was like an Amazon interview problem. It was like, you know, rotate a matrix by 90 degrees was literally the problem with the LeetCode medium. And I remember that trick of like, you know, just transpose the matrix and then reverse every single array in order to make the equivalent solution to having rotated the matrix at 90 degrees clockwise. I can just also show just how this would have worked. So like, you know, step one, you know, transpose matrix. So the very first thing I'm going to do is like, okay, for my box, right, for the box, essentially what I'm going to say is like, hey, this is going to be a new row, a new matrix, where it's like, you know, for each row inside the box, right, for row in box, I'm essentially going to apply the horizontal gravity, right? So here we're going to do self dot apply horizontal gravity row. Okay, so LeetCode is doing the weird thing again here. Okay, but essentially one thing I can do is like, okay, now that we've gone over like, applying the horizontal gravity, we can apply the horizontal gravity for every single row, and there we go, bada bing, bada boom, right? And so here one thing I can do is like, okay, why don't we do this? We'll just do return box, right? Right now we can't just return box, right? Because we've applied gravity from left to right, which is good, but we have not actually transposed we have not actually rotated the matrix 90 degrees clockwise in the way that we want, right? Here essentially we have one row with dots, hashtag, hashtag, but here we want one row with dot, one row with hashtag, and one row with hashtag, right? And same thing over here. Essentially here we have the output, like you can notice, like, this dot is this dot, this hashtag is this hashtag, and it maps, crisscross applesauce every single place, right? So we're close, but we're not there. And so essentially the thing that we're missing is to rotate the matrix 90 degrees clockwise. So one way you can do it is using the zip function if you know how the zip function works. But if you don't, then here's the way you could have done it, right? So step one would have been to transpose the matrix. Step two is reverse every row in the matrix, right? So the very first thing is like, get your dimensions. So m comma n is equal to length of box comma length of box of 0, right? And so here it's going to be transpose box is going to be equal to a new matrix. We'll put -1, and then here this is like usually we'd have this, right? It's like it's an n column row m times, right? Because there's m rows in total, right? But here instead of that we're gonna say, hey, there's going to be n rows in total now, and each row is going to have m columns, right? The point is that you flip the dimensions of the matrix here, and essentially what did I say? Essentially what used to be the old box of ij becomes the new box of ji, right? So here this will become transpose box is equal to a row. And the elements of the row is going to be box of I, j, or I in range. So here this will be box of ji. For I in range, so here we want to do times m, and for j in range n. Right? Wait, I gotta think about this. Right, so now we want m columns. Okay, I'm doing this one way. So here I can do print box. For row and box, print row. Here we can print out, apply transpose, dot, dot, dot. And then say for row in transpose box, print row, right? So here we can get rid of this. So here I just want to make sure that I'm going to end up doing things correctly. So here it's like, okay, so we applied the transpose correctly, right? Yeah, so here if we did n and m, right? ji. Yeah, because this is, yeah, there we go. Right, then we will have essentially done nothing, right? But if we do, this is weird because I usually have, yeah, but yeah, okay, I'm now starting to confuse myself, which is just weird, right? But the point is that these are the columns, right? So here we can do for j in range m, for I in range n, right? And this would be like, box of ji. But the point is that, like, you flip them, right? What used to be the old box of ij is now the new box of ji, right? And so here's like, you do, instead of having, n columns and m rows, right? So yeah, a value for n columns, per row, there's n values, right? And then m total rows. Here it's like now each row has m total of values, and there are now n total rows, right? Where n used to be the old number of columns and so on. So the point is that you flip the dimensions, right? And then like, you assign the values correspondingly, right? Whereas like, what used to be index ij is now index ji, right? And so that's essentially what I'm trying to explain. So sorry if I wasn't not doing too good of an example here, but the point is like here I print the things, whereas like here I print the box. So this is box. And then after I apply the transpose, here are the rows of box, right? So we can see we have transposed the box, right? If I do case 2, for example, here's like we had 2 rows, right? Each with 4 values. Now we have 4 rows, each with 2 values, right? And then you'll notice that again, the very last thing that we need to do is reverse every row in the matrix, right? So where it's like the very first expected element was hashtag dot, and now here it's dot hashtag, because again, we haven't reversed all the rows inside of the matrix, right? And so here we're gonna say is like, okay, we can comment this out. In fact, we can get rid of this. Right, now we have the transposed box, right, which is exactly what we wanted. And then here we can say, okay, we're going to reverse every single row in the transposed box, right? So here we're going to return every single row. So for a row in transposed box, but we're going to reverse the row, right? So here is going to be row in reverse for every single row in transposed box, right? So here we return a list with every reverse row, and there you go. You see that this works. I don't want to press submit here just because, okay, I just submitted one with 99.68%, so I don't want to lose that on my lead sync on GitHub, because you know that's just too clean a solution, right? But if you don't know how to use the zip function, which obviously does this a little bit faster, right, then the way you could have essentially solved it is to rotate the matrix 90 degrees clockwise. Essentially, hey, take the transpose of the matrix, and after you do the transpose of the matrix, reverse every single row in the matrix, and then you'll have effectively done a 90-degree rotation, right? And so that's essentially the other way that you could have essentially done that, right? But otherwise, I'll keep my solution as is. I have that beautiful 99.68% submission, just mwah, chef kiss, and there we go. So hopefully that solution made some sense, and yeah, so that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment, but otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.